Hi, everyone, and welcome to the June AIML Seminar Series. I'm your host, Ryan Felton from NASA Ames Research Center, and today I'm happy to have Jeroen Audenaert here with us. Jeroen is a research scientist at MIT, and today he will be discussing his work on foundation model development for NASA's Transiting Exoplanet Survey Satellite, also known as TESS. Foundation models are a growing priority across many fields, and NASA has established a 5+1 FM and large language model strategy to produce at least one FM for each of the Science Mission Directorate divisions. And there are new versions funding calls for Moon FM and Mars FM. With that said, Jeroen, please take it away.
You. Well, great to be here, everybody. I'm looking forward to afterwards having a discussion on if you have questions about any of the things that came up as well. So I'm very excited today to talk about how we can actually develop foundation models that actually take instrument systematics into account. Because as we all know, what we aim to do in science is make very precise measurements. But the bottleneck here is, of course, our instruments, and we need to be able to characterize the bias that we obtain there from different types of, like, for example, in the case of TESS, stray light or other types of systematic effects that can, that can introduce slight changes or things that shouldn't be there in our observations. And I'll start first by actually introducing TESS. Most of you might have already heard of TESS, but TESS is the Transiting Exoplanet Survey Satellite, was launched in 2018. So we're currently in extended mission 3. And the mission itself consists of 4 different cameras. You can see them here. And each camera essentially consists of 4 CCDs that record the different types of observations. So at each given point, we observe around 4 or 5% of the sky, and we do that between 27 days to 54 days at a time. Most of it was always at 27 days, but we had a couple of longer sectors. So one of those months is called a sector. After 1 month of observations, we essentially switch to the next field of view, as you can see here, and in that way we survey the whole sky. So we have plenty of data with TESS. On each given month, we observe between 2 to 10 million stars, depending on how faint in magnitude we go down to. And so it's clear that in able to process all these observations, we definitely need machine learning, because we can just not do all of this manually, essentially. And that's why we're actually building all these different types of machine learning model for TESS. And one of the main science goals for TESS is, of course, the planet discovery, but you have plenty of other things on the astrophysics side, such as the different types of stellar variability, and in particular, astroseismology. So you can see here a couple of examples of the type of science we can do with TESS. So you have pulsating stars. These can be radially, non-radially pulsating. And then you have binary stars. You have supernova. You even have asteroids that we can observe with TESS. And then, of course, transiting planets. And so the idea also behind developing these foundation models is that we can use them for a variety of science cases, and we then don't just need to actually start training our machine learning models from scratch anymore. And more recently, this was not driven by machine learning, but I do want to highlight this. We actually repointed TESS for the first time in its mission to observe the comet 3I Atlas. So you can see here a very cool animation made by my colleague Daniel Mutakrishna, in which we pointed TESS to observe this comet. Now, one image of TESS, you can already get some ideas of how it looks like, but one image of TESS essentially is this, right? So you have the 4 CCDs and the 4 cameras, and then in order to extract all the data, we zoom all the way in to get these different types of light curves. So each month, we get on the order of, let's say, 10 million light curves, and we try to classify all these different light curves according to finding planets, finding different types of stellar variability, as you can see here, for example, a binary star. So we have multiple machine learning algorithms running. One of them some of them are running on like the light curve classification itself and a parameter estimation, but others are also running on the raw images. For example, how can we build models that better correct the bias that we observe in these underlying images? And then if we can correct those, then we can also propagate this to our final light curves models that we can extract there as well. So in particular, what a lot of my science focuses on is on variable stars. You can see here a couple of light curves. The light curves are shown on the left side in black, and the amplitude spectra are shown on the right in red. So you can see the top two are two different types of pulsating stars. You have a delta Scuti star and a gamma Dorado star. So one is a bit higher frequency, the other one is a bit lower frequency, and then you have rotational variables and binary stars. So in some of the first machine learning project that I started working on a long time ago, we actually built a stellar variability classifier as part of the TESS astroseismology consortium to start classifying first Kepler data and then ultimately moving to TESS to build a whole catalog of what all the underlying sources look like in TESS. Now, one of the big problems, of course, that we're all aware of with plenty of data sources is that there are all these systematic effects, right? If you take an image of TESS, for example, at a single point in time, you can see it on the left, like a full frame image, you see this glare over there. For example, here, this is caused by stray light from the sun that reflects off the Earth and the Moon into the lens suite of TESS and then into the detectors. So imagine we're trying to observe a planet transit right here in this blob. It's going to be very challenging. So these are ways that we definitely need to correct for. And if you look at this top part, you can see like what one of those sudden glares looks like. You have a massive increase in brightness. So if you want to look for a planet at that point, it is very challenging, right? Other things that we really need to account to in TESS is crowding, because TESS has very large pixels. We often end up like extracting a light curve that is actually a combination of multiple separate stars. A couple of years ago, there was even a paper actually that thought they had discovered a new type of star, but in reality, it was just a combination of multiple different separate ones that looked like a completely new one. So it's very important to take into account these different effects. I won't really be focusing on the blending here today, but I will be focusing among others on like scattered light and other types of more systematic effects that are introduced at the image level and at the time series level. So the way we've traditionally been developing our machine learning models, as I said, is we train one model per task. We train a stellar variability classifier. We train one for extracting a stellar parameters. We train one for variable stars. We train one for transients. We train one for exoplanets. So we have all these different types of models, right? And they all work pretty well, but they're often just used for their single point. So we really need to think ultimately of how can we all merge this, and specifically with a foundation model. Before moving into the foundation model part, I'll just give you a little bit of background of what we've developed so far on the single model task, and then move into how we actually use this as the basis to develop more complicated models. So the first one, as I said before, is a stellar variability classification. So you can see a couple of light curves here, and these are actually still from the Kepler mission, but you can see what they look like. So you have, for example, aperiodic stars. They're just aperiodic on the time scale of 27 days, so it's a human-made classification. But then you have like delta Scuti stars, the third one on the left, and then you have other ones that are much more sinusoidal, like contact binaries, or on the right side you have auroral iris. So we've developed a bunch of classifiers actually to be able to find all of these in TESS. And recently, originally we started with developing feature-based classifiers, for example, random forest classifiers, but recently we've upgraded this to more quick algorithms such as transformers. And one of the undergraduates working here at MIT actually developed a new classifier called Astrofire, based on a transformer and a CNN-based architecture, where we could actually run this very rapidly. It takes on the order of 0.001 seconds to classify a single light curve. And it has really accelerated our ability to actually find all of these different types of variable stars. So here the classifier itself is getting on the order of 90% accuracy, depending on what particular class you look like. And if you inspect the embedding, you can see here the UMAP reduction, and you reduce it to 2 dimensions, then you see, and that's nicely able to separate those different types of stellar variability classes. And this project itself delivered already 4 million classifications in the TESS Kepler field of view. It's based on single sector light curves mostly, but then we started expanding this as well with a student from KU Leuven in Belgium, Nick Kliapets, and he actually extended the light curve classifier together with and added some other features as well, and therefore actually use all the light curves that we have in TESS in the Plato field of view. So Plato is an ESA mission similar to TESS and Kepler, more to Kepler, I will stare at the same patch of sky for a longer period of time. And TESS has already observed all of those light curves, right? So essentially what we did is we used the stellar variability classifier from TESS and classified 41 million light curves of 7 million sources to develop a massive catalog there. And this was actually used then for the astroseismology community as well to make guest observing proposals for Plato on which targets should be observed there. And that's very cool that we can actually use machine learning and TESS data to actually inform the selection of of what should be observed next. And I think that is really a very cool thing. But one of the problems here in all these models that we developed so far, and that often comes along, is again that we have these instrument systematics, right? So a lot of the classifications that we find are dominated by instrument. And you can see here in gray is actually the light curve. In green, you have the amplitude spectrum again, but then you see like towards like 1350, you can see that there's like these drops and these weird things happening in the light curve, and those are actually systematic effects. So a lot of our data are dominated by this because they are, for example, scattered light has affected this. You have other problems as well, but this is what we often see happening there. And so there are a couple of different ways to be able to deal with this in a regular classifier. One of them is, of course, just create a class, labeled class, where each of the examples actually just contains a lot of these systematic effects. But then, of course, if you also have other actual astrophysical stellar variability patterns, this might create some confusion there as well, and I will just select the dominant one. So that actually allows us to lose part of the information. So this is probably not an optimal solution in the long run, but at least if you want to productionize something, this is what is most often being done. You just create a class of separate instrument variables. Now, what you actually want to get down to is that the key thing, like to actually train any of these models, you want to be able to capture what's actually driving all of this, right? So you want to be able to capture what's driving the physics. You want to be able to capture what's driving the instrument variations as well. And all of this at the bottom goes down to develop, if we're developing these machine learning classifiers, it just gets down to developing proper representations. You have a physics representation, and currently what you assume is that everything is driven by physics there. But this is not true in reality as well, right? And on the representation learning itself, before diving into what type of cooler representations we can learn, traditionally, of course, you had feature engineering, where we developed these Fourier transforms, where we had to calculate the Fourier transform and then fed all of that to the classifier. But then more right now, of course, you have much more fancy ones, which rely on deep learning to actually start calculating these different types of neural networks. And the idea, of course, behind these representations is that right now we have all these separate models, but ultimately what we want such a representation to capture is just the thing that's driving the physical properties that we're seeing, right? And it doesn't matter whether I want to predict the stellar variability class, the stellar parameters, it should be able to capture those with one model. So we actually want to make all these separate models, stellar variability classifier or stellar parameter determinations, like have some kind of shared structure, because they should be able to pick up on the same thing. And then additionally, we wanted to capture the instrument variations there as well. And that, of course, brings us to the topic of foundation models. And I think a lot of you have heard about this or are working on it yourself too. But the idea here is, of course, that we train such a shared representation that can then be used across a variety of tasks. So we have this representation, and we can use it for whatever we want: stellar variability classification or stellar parameter determination. And the most important thing is that we want to leverage unlabeled data. And the reason is because in the case of TESS, for example, we have hundreds of millions of unlabeled light curves, but only a very small fraction of those are confidently labeled. So if we can take advantage of all the unlabeled data, that really becomes very powerful for our machine learning algorithm, because then we can start learning such representations without us actually having to first provide labels. Okay, this is a delta Scuti star, this is an eclipsing binary, or this is a planet. No, we just want to learn a representation that's completely separate from the ultimate downstream task that we want to do, because we assume that the physics driving those tasks as well is already incorporated in this first stage. And one simple way, or one way that's often is being done, is by creating these so-called surrogate tasks. For example, you can actually train your model, like if you have a masked autoencoder, where you just start masking parts of your input, and you actually train your model to predict those. And then by this way, by masking it and then predicting it, you kind of have your model learn the underlying dynamics of what's happening within your time series, or in this case, what I'm showing here in the example, within your image. Now, one other strategy is contrastive learning, and that's the one we actually started using for our specific model as well. So traditionally, if you train your supervised machine learning model, what you do there is, you know the labels, right? You know whether it's a cat, you know whether it's a dog. But if we're now training everything unsupervised, we don't know this. We don't know what's a cat, and we don't know what's a dog. So what we need to do is we provide some augmentations. So you take your random image of a cat, and then you, for example, get a grayscale image and a blue scale image, and you tell the machine learning algorithm to put these two closely together in the latent space and say that they should actually be clustered together. And by this way, you have some kind of surrogate task as well that actually allows you to train your machine learning models. Now, one very cool thing, of course, is in astronomy that we have a lot of natural augmentations, right? And this is cool because if you're observing a star, often you have observed that star in like with the same survey, you've probably already observed it. Maybe with a different telescope, you have observed this as well. So we don't have to augment these things with like fake data, but we can just use natural augmentations. For example, an observation by TESS, an observation by Kepler of that same underlying star. Or in the case of galaxies, you could have HSE observe something and then the legacy survey, for example, as well. So this can be one very cool way in which we use the natural data from astrophysics by having all these overlapping observations to train your machine learning with contrastive learning, rather than actually having to augment your original data. And here I'm just again showing like what this looks like for a consumer-based model. So this is not astrophysics related, as you can see, but essentially you have all these texts and, for example, describing images. You have speech, all kind of describing the same phenomena as well. You train your foundation model on this, and then you can use it for a variety of downstream tasks. And it's exactly the same in astrophysics. We have all these surveys that are ongoing. So you have James Webb, you have Gaia, which we'll get more data from soon. You have TESS, Kepler, and now in the future we'll have Roman as well very soon. And then we have all these ground-based data as well, right? And by combining all of the available data, I think that's really very powerful. Then we can actually create these large models that can be used for a variety of tasks. And one of the first ones in astronomy was, for example, AstroClip, where you actually have, for example, galaxy images, you can see on the left here. So you can encode these. And for the same galaxy, you also have a spectra. So we can say that these should actually be put closely together in the latent space. And in this way, we can combine all of the available data there. And this model was later upgraded, so it's being led by Polymatic. It's associated to like the Simons Foundation and the CCA. Recently, they released, for example, Aeon, which is also a large foundation model where they threw all of these different data sets together. Didn't do it in a contrast, but I think that, if I'm correct, I think they did it generatively as well now, and essentially kind of upgraded it and threw all these massive amounts of data together to train a very large model. And then you can use that large model for a variety of your downstream tasks, for example, morphology classification of galaxies, which is one of those downstream tasks. And these are the astronomical or astrophysical foundation models that are people putting together, but you don't necessarily need to stay just within astrophysics, right? You have other types of foundation models that were not developed for astrophysics at all. But they were, for example, developed for time series. And Moment foundation model was one of them. So it was trained on, among others, like ECG signal detection, human activity on a bunch of different time series. And then the idea is that you can afterwards apply it to any possible type of time series because it has learned to capture dynamics of some of that behavior as well, what can happen in different types of time series. And I have seen plenty of them. So when we saw this, our question was, okay, can we actually apply this to astrophysics as well? And it turns out we can. So one of the undergraduates, Alice, she started working on this last year, and she applied this Moment foundation model, and she saw that we got on the order, I think, between 60 and 70% accuracy without actually even fine-tuning them all. So just giving it astrophysical data, we're actually able to separate according to the different types of stellar variability. And of course, as I showed before, like in our supervised classifier, we get 90+% accuracy. This is much better. But given that this type of machine learning algorithm has never even seen astrophysical data, it's actually doing a relatively good job. Of course, pushing it to actually reach 90% accuracy is a different question because it was not designed specifically with scientific time series in mind. But it's very cool that we can actually use these types of foundation models developed commercially at least and try to apply and get some results already in astrophysics. They're definitely not perfect, but at least they're getting there. And the reasoning there is also similar to a project we did a couple of years ago where we took signal processing techniques and machine learning techniques developed for ECG signal classification to distinguish healthy from sick patients based on their heart rate. And then we actually showed that you can cluster different types of pulsating stars based on their near co-rotation rates and based on their classes with this exact same technique. And this is because the only thing that actually these algorithms care about is being able to capture on all these underlying dynamics of the time series. And that's very cool that we can just work so interdisciplinary there. Now, of course, as I said before, like if we just use these foundation models blindly, just to, assume that we can just throw all this data in there together, that is not going to work, right? And especially in the case of astrophysics here, we're like with the time series foundation model, we're only getting like 60% accuracy. Even if you take something like Aeon, as I showed before, you're getting pretty good accuracy, but it's definitely not perfect. And one of the big reasons is because they don't necessarily take into account instrument information in the correct way, we believe. Um, and that is because, like, if you're observing a signal, right? You have your signal that you can see here, and that always consists of your target phenomena and your systematic effects. So if you, let's say you have a sinusoidal time series, is just then your signal is a combination of this sine wave plus some systematic effects. In the simplest form, just a linear trend that gets added, but in reality, in the case of TESS, we see much more complicated things, right? And if you do this on the image domain, you have similar, you have some background, or maybe it even distorts part of your image as well. So it's always a combination of how we're measuring something versus what we're measuring. And I want to bring this back to TESS, right? So if you're observing, if we're making observations, as you can see here, we often have the scattered light, as I mentioned before, and you can see what happens here, like on actually a movie here, and you can see you have these sudden glares appearing. And if you're looking for something in that glare, it's very tricky to actually find this. So we really need to take into account such effects. And if you look at the data a little bit in more detail, as you can see here, so you here see a number, so the colors just represent a bunch of different sectors, and then the rows are just all individual light curves. And essentially, black represents that it's just masked out because there was something happening, the data quality wasn't good enough, or something didn't happen, or there was a NaN value, for example. But you can see that a lot of these black gaps, there's just a lot of bad data points that were filtered out because, among others, stray light actually. So you see this also varies on a sector by sector basis, depending on what's happening there. So you can definitely see how much instrumental effects are biasing our final data, right? And so the question then becomes, okay, what happens if we don't take these instrumental effects into account? And I think one of the coolest things that we actually, or one of the cool things that we saw is a paper by Euclid here as well. So Euclid, the European mission, they trained a foundation model. And you can see here, if you translate that, if you take the latent space and you plot it in 2 dimensions, you can actually see the embedding over here. And it's very cool that you can actually see that all these galaxies are nicely clustered together and actually have some correlation according to structure and shape there as well on that foundation model. But then if you start looking a bit in detail, you also see that you have these 2 separate clusters here on the right, and those are actually dominated by instrumental effects. So it's cool that the machine learning algorithm actually splits these out already. But the problem is, like, if you take one of these images, for example, and you have one observation, that's fine, because they will be separated out because they look slightly different. But then you start making multimodal, or you start adding other data, you're kind of saying, okay, these two images are exactly the same, and maybe one of them is distorted heavily by instrumental characteristics and the other is not distorted at all. So you're kind of putting systematic noise together with just actual physical observations, and that can become problematic, especially once we start scaling this up. And that's the reasoning why we also start working on some of these projects afterwards in more depth as well. So the question becomes, how can we overcome this? Now, the very cool thing is that actually it turns out a lot of these instrumental properties, which I hinted on before, is actually they vary over time. So if you look at the case of TESS, so you can see here the top row, this is from the first 2 years of observations. So you have the same star, but observed in 2 different months, so 2 different sectors, sector 14 and sector 15. And you can see the physical properties look very similar, right, just based on this. But if you look in more detail, you also see that the systematic effects are quite different. So you can see here, like on this right one, you have a larger gap in the middle, and then you have like these 2 slight downward slopes affecting each of the different orbits that constitute the sector as well. And if you then compare it to Kepler, so the previous mission, then you see, well, that data is much less noisy as well. So we can actually take advantage of this because the physics kind of stay the same, but the instrument properties vary. So if we can take advantage of all the overlapping observations, that's a way for us to kind of learn how and build a model that can actually learn to separate these out. And just if we only look at TESS already, we have a bunch of observations, right, overlapping observations right now. So the colors show how many observations a single point has. So you can see here, some of them even go to 40 overlapping observations. in that continuous viewing zone as well. As you can see here, that's where we have a bunch of overlapping observations. So we can really use this to our advantage and learn to build survey-agnostic embeddings. And what do I mean by this? Like with a typical foundation model, what you assume again is that everything is physics. So if we are training a machine learning algorithm, we're training our foundation model, we're not using any specific label, but what we're saying, we're applying contrastive learning. Let's say we take a random star, number 99, observed in sector 41, and then we take that same star, but observed in a different sector. We're just saying traditionally, okay, this should all be put together in that same physics latent space. But in reality, of course, if you look at it, the physics look similar, but you again see that these things are slightly different, like the instrumental trends are a little bit, or different between these two. So what we then can do is actually take this to our advantage and build this thing called a causal foundation model. So what we do is we create two separate latent spaces. We have a physics latent space and we have an instrument latent space. So what we there again in our physics latent space, what we do is we just take that original star number 99 and we just match it with another observation from a different sector of that same star and give that to the physics latent space in this contrastive approach. In the instrument latent space, what we dare say is we take any star observed in that same sector, sector 41, for example, and say in the latent space and the instrument latent space, these two things should be put closely together. And if you look, they actually share some kind of similar systematic trends. And in that way, we learn to disentangle the physical effects from the instrument effects. And then what you can do is you can use this physics space actually to make your analysis much more accurate because you've been able to remove these systematic effects. And then your instrument space, ultimately, you can first of all use to better understand the instrument. But if you would transform this into a different type of model, for example, generative model, you can do it automatically. But then you can also use this as an instrument model that you can ultimately go back to and correct your raw data with. And now, after I've shown this architecture, I just want to show you a couple of results there as well. We first validated on simulations. So you can see we just simulate everything to make sure our architecture actually work. As you can see what the type of simulations look like. In the middle, for example, you see if you look at the black line, that's actually the observed signal, but it comes from this red signal that we simulated first, and then we applied like cutoff. We applied a rather complicated instrument noise model as well, such that we could actually learn to disentangle this. And then if we look at the results, it turns out that our model is actually able to separate these out pretty well. So on the left column, you have the stellar space or the physics space, and on the right column, you have the instrument space. And if we look at the top row, and we color code this according to the sector or the instrument configuration number, we see that the stellar or the physics space doesn't show any specific correlation at all. But if we look at the instrument space, we see that it's nicely separated out. And there we see that it actually learned the instrument component. If you then look at the second row, you see in the stellar space that there is a nice correlation according to the stellar parameter. In this case, again, it was a simulated one, but you do see it captures very nicely. If you look at the instrument space, there is still some that it has not completely learned to disentangle the stellar parameter from this instrument space in this case. So there's definitely still some correlation happening, but it depends a little bit. We've now also been able to actually reduce this significantly, and now we don't see much of this correlation anymore. This was one of our initial studies. So we've actually very well able to disentangle these. And if you look at it more quantitatively, rather than just in UMAP space, these are the results. So if we afterwards fine-tune our model and we give it actual labeled training samples for different types of downstream tasks, in this case to predict a stellar parameter, we can see that our model, the red one, actually outperforms any of the other models. So the red is our causal foundation model, where we then train an MLP on the physics latent space to make a prediction, and we see that we kind of outperform by 10 to 20% actually a traditional foundation model, the green one, or by even much more the purple one, as you can see there. And then we also applied this model to TESS already. These are just some preliminary analysis, but you can see that in the case of TESS, the right one here is actually nicely able to separate out the different sectors already. And if you color code the stellar latent space, there's not much correlation happening there. But this is still ongoing work for TESS, so this part is not published yet. But one very cool thing is if you look at one of these plots and you actually analyze the stellar latent space for physical properties, we nicely see that it actually captures the near co-rotation rates of stars very well. If I'm not mistaken, this one was made for gamma Doradus stars and hybrid pulsators. So you can nicely see it actually learns to pick up on this. And so this is very cool that our architecture actually able to capture the near co-rotation rate, meaning that we could maybe ultimately on the astrophysical side use it to get better insights and like maybe surface rotation as well, and then also the near co-rotation and see whether something is happening there for maybe angular momentum transport. So it's very cool that our model can capture physical properties. So this model was based on the contrastive learning, as I said before, but we also started transforming it into a generative model over the past year. And this work was being done by our PhD student, Pablo, here at MIT. And rather than sticking to time series, we took one step back first, and we wanted to validate it on imaging data, because if you work with the machine learning community, it's much easier to actually show how well something works on images compared to time series, and it's also easier to capture the dynamics, because time series models are a whole thing on its own, and a lot of different complications come in. So we just really wanted to show that this model worked already on imaging data. And in this case, how we changed the architecture is we used data from the legacy survey, DESI, and then HyperCam, so HSC, as you can see here. And we use the same idea, right? We have these triplets of pairs, so we get an anchor image, but we actually, in this case, don't feed the anchor image as input to our encoders. What we just do is we generate this anchor image, so let's say galaxy number 99, observed by HSC, to retrieve another image, the same galaxy, so number 99, but observed by legacy survey, and then an image of that same instrument as well. We feed that to our encoders, and then what we do is we actually use that anchor image to as the final target or anchor as a final target image, essentially using a flow matching algorithm as well. So we don't use it as input here, but we just say, okay, using these two images and the encoders, then you should be able to actually get to this anchor image back. And the results I'm showing here in the next slide, it actually seems to work very well. So you see on the left side, you see the physics latent space, color coded according to HSC and legacy survey, and you see there's no specific correlation at all. And then the colors and the shapes actually represent the different types of galaxies, just to show that they are rather closely matched together. On the right side, you then see you see the instrument latent space, and we can nicely see that the two instruments are actually separated. So it has learned to disentangle these. And then the very cool thing is that we can also, of course, use this for anomaly detection. And this is important because in the case of many astrophysical surveys, what we really want to do is find these weird looking things, right? Because if we train, currently what we have in production, for example, in the case of TESS, is we have exoplanet detection pipelines, and they can find very well the known types of planets, right? Because that's what we've given them as example. But to find these weird things of planets, to find weird planets or weird types of stars, we really need to have these methodologies that can do anomaly detection. But traditionally, most of what these actually return are driven by instrument or systematic trends. And this algorithm now, this generative version of our instrument, disentangle, actually seems to be able to work very well for anomaly detection. So if we use our latent space, our physics latent space on the left to find outliers, then we can actually see that all of the retrieved ones are galaxies. Now, if you look at Aeon, on the other hand, you can see that a lot of these are actually dominated by different types of instrumental properties, as you can see these different colors. And if you look at our instrument space, you can see obviously almost all of it is also dominated by different types of instrument. So it's very cool that we're actually able to find these unique types of, to find these anomalies instead of just instrumental versions. And specifically what we aim to use it in the case of TESS for, so we're also working on adapting this for TESS, is now to find more things like these disintegrating planets, because this one was found I think 2 years ago by my colleague Mark Hahn, and it showed a rather interesting light curve. But like our traditional algorithms might not have picked up on this, but if we have an anomaly detection, once we want to use that to actually find more of these disintegrating planets, and among other things that we are currently not aware of. And that's really one of the main drivers, is we want to have anomaly detection methods that can actually find novel types of stars rather than just return as weird instrumentic trends that we're not necessarily interested in from an astrophysical side. And then on the instrument model itself, what we can do with that is we can actually use that to build a fully generative model of our instrument, and ultimately go all the way back to correct our original data for. So if we nicely know what's happening over there, we can apply that correction algorithm to our raw data and also produce better output for the community there as well. So you can see here, for example, if we go from the ground truth on the top row here, and then we start reconstructing to actually clean it up a little bit. You can see what happens over here to go from a low SNR to a high SNR essentially. And then, yeah, you can see on the bottom, you have some more example of the original and the corrected one, how you can actually learn these things. So this is definitely, we need to still work on applying this to TESS as well, but it's some great preliminary results as well. And looking a little bit further ahead as well, such a model where we use overlapping observation is also very relevant for future surveys, in particular for things like the Plato mission, which will have up to 24 overlapping cameras that are almost at the same time with a few seconds lag maybe, observing the same target. So you can actually learn the systematic trends of each of the individual cameras and then learn a better data-driven model to actually correct these and get much better predictions in the end there. So that's something we'll start working on as well with some collaborations in Europe that will lead this part, but it's very cool that we can actually use all these observations there as well. And ultimately, what I want to kind of allude to is that all the work we've done, like all the work that's happening on building these foundation models, I think it's very important that we start taking one step back and always think where the data is coming from. If you want to build foundation models, the idea is not just that you throw all of this data together, but that you rather do it in a smart way. And so one of the things we've been working on as well is actually creating a scientific time series benchmark so people can actually evaluate their foundation models across different types of scientific problems that are all dominated by instrument noise. So this was just recently submitted, but essentially, for example, here we've created benchmark, we've tested how well commercial foundation models are working on this. And then what we want to do is actually apply these instrument removal or instrument agnostic models to it to actually reduce the amount of instrument noise and make sure that we can actually allow for these different types of detections. And I think that's also the way to go, because if we just use commercial foundation models like these different time series one, they're not going to work out of the box to get the highest possible accuracy that we require for science. So we need dedicated scientific models to be able to actually assist us in our job as researchers. And that's something that we're working toward, actually building models that can reduce instrumental effects and give us better instrument models, and then ultimately help us accelerate our physical discovery. So yeah, this was kind of the summary of my talk. So if you have any questions, feel free to ask them. Thanks.
Thank you so much, Jeroen. This is very exciting. So we'll take some questions right now. You can either raise your hand or put them in the chat. Let me see. I definitely have a few questions I could start us with. So Jeroen, you spoke about some work that one of your students was doing where they were looking at essentially AI/ML techniques outside of astronomy. I think they were mentioning medicine.
Yeah.
And finding that there was applications within astronomy. So I was wondering a little bit about that experience of needing to go outside the field and kind of first just even find these other techniques, and then I guess I'm wondering what was it like to be able to try to bring it in and apply it within astronomy, because I would imagine it's not just plug and play.
Yeah, that's for sure. Actually, it's a great question as well. I think the way, like, I always think of these as just like data processing methodologies. I also, my own background, actually, I come from the machine learning side and not from the astrophysics side. So I was trained in more like finding these different types of algorithms and then finding the best one that works for your solution. So a lot of what my work in went and what the student was working on as well, just like looking, for example, through audio processing, looking through ECG signal processing, and just trying to see, okay, what type of underlying data that they have is similar to our data in astrophysics as well. And the first project I did was actually during my PhD. This is where I came across these ECG signal ones. And it was very exciting just to see, okay, my question was just, okay, can we apply it? And we just start working a little bit, but we definitely had to tweak a lot of the underlying algorithms as well and kind of make it work for astrophysics as well, right? So one of the first things was it's called the multi-scale entropy that we found there, and that worked pretty well in astrophysics, because it was just meant to kind of capture the complexity of any type of signal. And it was developed for biomedical one, but then you could adapt it here. And so what the student did then, kind of building up on this, is really taking like these massive foundation models, train on everything, and then start applying it. And I think the key thing is just to be very versatile and not necessarily look within the astrophysical literature, but just go completely think whatever data, underlying data is relevant, and then look for any type of model that's being built for that. Can be neuroscience, can be heart rate studies, anything that's very similar to the type of data you're working on. I think that's the key to actually accelerate research and like kind of work between different fields.
I like that a lot. I like it's kind of that like that de-siloing idea or like getting outside of your bunker kind of idea. We have a question from the audience. It looks like Haley, you raised your hand. If you want to just unmute or type your question, just go ahead.
So I just want to ask the question. Given that pre-processing pipelines are designed to suppress systematic noise, how do we ensure we are not also suppressing genuinely novel astrophysical phenomena that don't resemble anything in our training or validation sets?
Yeah, that's a great question, I would say. So it depends like how specifically or how these type of pre-processing pipelines are constructed as well. I think in the case of TESS, for example, right, as I look at what we're doing, like in thinking it's just separate from the machine learning part, so we actually have many different types of light curve pipelines happening. So we have QLP, we have Spark, and then we have now TESS Gaia light curves, you have community-driven light curves, and all these different types of pre-processing light curves actually use slightly different types of correction techniques. So all of those are actually are suited for different types of astrophysical studies. Like for exoplanets, you do very heavy detrending and you remove all type of astrophysical variability there. Now, if you want to study astrophysics, well, you shouldn't use one of those. Now, ultimately, like it requires a lot of training to know what you need to use at what point in time or for what type of scientific goal. I think one cool thing about what we could do with these types of machine learning models is actually we feed in like all these 10 different types of pre-processed light curves and together with a raw light curve as well, and then actually have the machine learning algorithm learn on the differences between these two and try to combine it in an optimal way. So essentially you treat them as different types of instrument configurations. Of course, the amount of data you have to put in your machine learning algorithm, it kind of grows exponentially the more you do this. But I think in that way, by just treating every product that's already there as an instrument configuration one together with the raw data, you can help the machine learning algorithm learn a little bit more quicker, while actually also preserving some of the original data that's not corrected yet, and have it figure out, okay, what are the optimal ways for what type of science goals.
Perfect. Thank you,
Just
Jeroen.
wanted to
Oh,
ask
sorry. Yeah, go
something
ahead. Go
again.
ahead.
Can I ask can I ask a second question because I really want to know it?
Yeah, of course. Yeah, please go ahead.
Oh, sure. Thank you. So, to what extent do our definitions of habitability reflect the limitations of terrestrial biology rather than universal principles? And how can we design missions that avoid this anthropocentric bias?
Yeah, that's a good question. I think like ultimately like for our habitability studies, of course, just looking at that, like for missions like TESS, for example, if we design more of those, what we want to be able to do is like if we actually design studies to find planets outside of our solar system, we need to be able to make sure that we can actually observe that we can do follow-up observations as well, right? Missions like TESS, those are just we're survey missions, and we need to follow up all of those missions afterwards as well with telescopes on Earth, or much more expensive with James Webb, for example, if we find interesting planets. So I think you kind of to be able to find habitable planets or whatever your science goal there is. You need to make sure we can. It's not just a single one, but you need to kind of look at all missions together there and be able to make sure that we have follow-up programs, you have detection, you have the follow-up together, and that's ultimately, I think, how we can start expanding there and finding more of these habitable planets.
Perfect. I have another question, Jeroen, and if anyone else has one, just again, type or raise your hand. You were talking about the science benchmark there at the end and kind of this whole thing of going from commercial and trying to kind of get away from that. And I was wondering, what what kind of timeline or like time requirement have you seen when taking a commercial tool and trying to essentially rejigger it for the science? And
Yeah.
separately, how long do you think it would take to do this kind of starting from scratch with your team, where you're not using a commercial one, and you're using something kind of more built in-house? Can you kind of give us a sense of those two different timelines?
Yeah, I think it's actually like on the commercial side, we're in a very exciting time in the sense that it seems that the last couple of months, I've never seen so many physics-driven companies actually raise money to build models that will, well, maybe replace physicists as well. But I think they will more end up assisting us. So there's a lot of companies actually working on trying to accelerate science in that way. I think in terms of timeline, if you take one of those commercial models, they usually do require a lot of fine tuning. I think you can get a very good base accuracy there, but then they're bottlenecked because they're on the one hand, they're incredibly large. They might be larger than what you actually need. So maybe they will have a more accelerated timeline where we can actually use more compressed versions. But then again, if you start from scratch, I think a lot of it is just like, okay, we need to have all the data in there. So just getting a team together, working across different scientific fields probably takes on the order of like 6 months already just to get all the data there. And then you need to start, okay, what type of commercial models are working and which ones are not working as well. And we saw that like a lot of the actual commercial models, they get good base accuracies, but we cannot really push them to the top compared to dedicated models. And I think like what the existing commercial models are developed for these general purpose problems, right? They're not really meant yet to actually tackle our very detailed science problems. So I think if there would be a lot of money coming in there from industry, we could definitely accelerate this timeline. But in my opinion, you need to have a lot of understanding of actually some of the underlying detector characteristics as well to be able to develop these models accuracy. And I think often when you're in the industry side, like if you have consumer data and stuff, it's much more easier to actually understand the biases there than in our case as well. And even like in the data sets that we release, like people usually just use like the flux information and the time information, but they don't dive into the underlying instrument properties. And like you actually need to be able to feed that into your models to have very accurate results. And so I think it's very complementary, these two, because I doubt like the commercial models will start going and acquiring all the available TESS information and making sure there is actually an option to input that in their models. So therefore, by developing or by leveraging the techniques that are at the basis for these large models, I think we can gain a lot of speed there. But then knowing where they go wrong, we can rapidly adapt and use that and build improvements upon that. So we can actually build better models on our own there as well. So I think they're really like collaborative. For like, if right now, if I want to do a quick analysis, I might just put it in like a foundation model that exists already. But then if I want to get detailed scientific results, I know I'll have to work with a team on that to actually get much better insights.
Okay, that's really good. That's really good insight to have and to hear. I guess there's one more, and then we can start wrapping up. I know a lot of what we were talking about today was very test focused. And one thing that kept coming back to mind was how well could either James Webb or, future habitable world observatory observers take some of this and apply it to their work? Like how much of this would be plug and play, and how much of it, again, kind of like with that whole commercial versus in-house thing, how much of it would be, James Webb observer analysis needing to take this and kind of retool everything for their specific pipeline?
So I think there a lot of the work would be focused on the encoders themselves. So like if you, depending on what data you're working with, you need to just have different encoders. If you're either working with an image or a spectra or a light curve, you need to be able to deal with like those slight differences as well. But ultimately, I think the underlying idea is very easy to transfer across different types of missions. like for example, with Roman, once it starts delivering light curves as well, I think it's very easy to start using this data and then using this model and start applying it to Roman as well. And it would be actually an interesting experiment if we have our pre-trained model from TESS already, and then we just keep feeding all the Roman data as well. How much do we actually need to fine tune? How rapidly will it learn these differences? Because the encoder itself, they can capture light curves already, right? The Roman ones will look different, but it won't be that too difficult to adjust it, I think. And in the case like James Webb, I think there's plenty of things to do there as well that we can also use it. Like, for example, one of my colleagues is doing a lot with stray light correction as well. So he's training like diffusion diffusion models to actually correct for the stray light. So just on the raw image level as well, purely focusing on that. But like that kind of gives you a lot of power if you, depending on what you condition it on. Right now, these are conditioned on the angle of the Earth and the Moon toward the satellite, but you could actually do it for a lot of different ones as well. So I think that would create a lot of unique opportunities to just transfer across missions, essentially.
Okay, that's really helpful. We actually have one. Looks like let's take one last question. We have one here in the chat. Are you able to see the chat, Jeroen?
I've not been able to see the chat yet.
Okay,
We'll see.
I can also read it to you. It's coming from Ania. They're saying, to build on the first question, choosing whether to consider adjacent pixels as representative instead of background can make a big difference when you have unclear borders. I often come across this issue in my own image analysis research where I do not know what each pixel the border of the object is. What is your process to determine the object edges?
Yeah, that's a good one. So it depends actually on the underlying pipeline there a little bit as well that we're using. So each of these pipelines have slightly different ones. So I think if I go all the way back to this first image, so I think this is what you're referring to essentially, like the different types of stars, I assume. So there, usually we use some kind of, we have the positions of the star as well, the position of the satellite, so they're nicely aligned. But then like to determine actually what the final mask is, it's some kind of arbitrary, well, not completely arbitrary, but some pipelines use like square masks, some use circular masks as well. And then if you have very bright stars, often you use some kind of clustering algorithm on top of that to see where actually those bleeds go out to. Like if the light would disperse all the way, so you have a couple of columns there as well, you need to have a clustering algorithm that automatically defines until where the light is actually going to. And it turns out that depending on what science you're doing, like do you go faint, do you go bright stars, all of those, you actually need slightly different types of underlying methodologies that can actually define that can find these different types of pixels as well. So it's heavily dependent on the underlying pipeline. By default, I think a lot of them just use like squared pixels. And then if you want to do more detailed analysis, often you start doing even custom masks. So the question is, do you do it for like a single star or do you do it for 1,000,000 stars? Because if you do it for a single stars, you can start optimizing for that as well. And then you kind of need to see, okay, what are the nearby stars in the field as well? There might actually be affecting the light that falls into, might they be falling into the same pixel as well. So it's not a trivial task, but each pipeline has its own strategy depending on what exactly it's focusing on.
Okay, thank you, Jeroen. It looks like we may have one more question. Ali, if you want to ask it here, you can, or you can always email Jeroen. But I think if there aren't any other questions, I believe we can start wrapping up here. Jeroen, thanks again. This was fantastic. I'm going to stop the recording right now. 1 second.